Hello and welcome to this lesson on lattice enthalpy. The first thing we're going to do is come up with some definitions for each of these key terms because they're very important moving on to be able to construct something called a Born-Haber cycle. So to begin with, we've got lattice enthalpy, which is given the symbol delta LEH. Now anything with delta H means enthalpy change. The LE stands for lattice enthalpy, and this little symbol here means that it's done under standard conditions. Sometimes the H is written before the LE or whatever other symbol you put in there. Both are correct. Now the definition for lattice enthalpy is it's the enthalpy change that accompanies the formation of 1 mole of an ionic compound from its gaseous ions under standard conditions. So what we're doing is we're taking gaseous ions that form that ionic compound and going straight to the solid version of the ionic compound. So an example of an equation that shows a lattice enthalpy would be to take gaseous potassium ions, gaseous chloride ions, and then end up there with solid potassium chloride. Okay, so if you look at that equation, read that definition, they should match up perfectly. Next up, you should have come across this definition before in Year 12 or AS Chemistry. This one is the standard enthalpy change of formation. Delta H for enthalpy change, standard conditions there, F for formation. So you should know this one as the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions, with all reactants and products in their standard states. So if we're going to try and form solid potassium chloride, then all we need to do is have a balanced equation to form 1 mole of potassium chloride solid from whatever elements that's made from, so potassium and chlorine. So our equation would look a little bit like this. So we've got solid potassium here because the solid is the standard state for potassium. And we've got chlorine here. Now remember the formula of chlorine is Cl2 because it exists as a diatomic molecule, also as a gas in terms of its standard state. But I've written a half in front of it here because you'll note that potassium chloride only contains 1 chloride ion. So I only need half stoichiometrically of the chlorine there in order to form that product. Because these equations, standard enthalpy change of formation, have to be balanced to form 1 mole of that compound, hence the half here. It's not saying I've split a chlorine molecule in half, it's just saying that to balance that equation I would need a half. Next up, we're going to have a look at the standard enthalpy change of atomization. We use an AT in the symbol here, delta H as always, for enthalpy change. Now, this is the enthalpy change that accompanies the formation of 1 mole of gaseous atoms of an element in its standard state under standard conditions. So you take the element in its standard state and you make atoms out of it. So an example of this for potassium would be that potassium exists normally as a solid, right? Giant metallic lattice, potassium, potassium, potassium. Whereas if it was to undergo the standard enthalpy change of atomization, then you'd end up with a load of gaseous atoms of potassium. Next up, in order to make atoms of chlorine, well, chlorine doesn't normally exist as atoms, it exists as diatomic molecules, Cl2. So to make 1 atom of chlorine that's in the gas state, you'd need to take half a molecule of diatomic chlorine, and that standard state there is in the gas state. So effectively, when you're making gaseous atoms of a substance, you are actually breaking the bond, but you're not necessarily forming an ion straight away. That's quite important to note. Next up, we're going to have a look at the first ionisation energy. You should have come across this again in Year 12 or AS. And this is given delta HIE for ionisation energy. And the definition of this is the enthalpy change required to remove 1 electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. So an example of this would be that if you were to take gaseous potassium atoms that you could have formed previously, by the way, via the enthalpy change of atomization, it's the product of that, then you would end up with gaseous potassium ions plus the electron there that has been removed. And remember that there's not just first ionisation energy, you could have second ionisation energy as well, where you'd go from K plus to K2 plus 2 electrons, as it were, if you'd remove 2 electrons from it. And obviously potassium doesn't form 2+ ions, we'd probably be looking at that more for something like magnesium or calcium. But remember that second ionisations, third ionisation energies all are possible as well. Next up, this is the one that you haven't come across before. It's called first electron affinity, and this is given EA, it's in the game for the symbol there. And this one's definition is the enthalpy change when one electron is added to each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1 minus ions. So effectively, guys, this is just reduction, and ionisation energy is just oxidation, right? But they get fancy terms when we apply it to the enthalpy change. So this time we're probably talking about non-metals, right, that get reduced rather than oxidised like the metals do. So let's have a look at this with respect to chlorine. So we've got to go from a mole of gaseous atoms, so I've shown a mole of gaseous chlorine atoms here. I've not shown them like this here, Cl2, because that's not been atomised. Remember, it's only been atomised when you broke the bond. So I've got to add a mole of electrons to it, and then I'll form a mole of gaseous 1 minus ions. You could also have second electron affinity as well, which is when obviously you reduce it for the second time to form a 2 minus ion. But you'd already be starting with a 1 minus ion in the second electron affinity. Right, let's move on then. So today we're going to be looking at something called lattice enthalpy, and I want to get an idea of what lattice enthalpy is to begin with. So we've already described its definition. It's the enthalpy change that accompanies the formation of 1 mole of an ionic compound from its gaseous ions under standard conditions. Now let's try and visualise this. So here for sodium chloride, the ionic compound, most classic ionic compound that exists, table salt. People used to get paid in it, hence the term salary, which you've probably heard before. That stems from a Latin word for salt, or the expression you're worth your salt. Anyway, let's carry on. So we're taking gaseous ions here of sodium and chloride, not sodium and chlorine. Remember, the ion of a non-metal ends in "ide." And we've got to form 1 mole of that ionic compound. So I'm going to have an enthalpy change here that's associated with forming 1 mole of that ionic compound in its ionic lattice structure. Remember, up here there is no lattice, and here there is a lattice. So effectively this shows the formation of bonds as well in the giant ionic lattice, and there's an enthalpy change associated with that. So what type of enthalpy change are we showing here? Well, this is going to be an exothermic process. One, because the arrow's pointing downwards. Okay, and whenever we point an arrow downwards in any kind of energy profile, we're referring to a negative change there, energy being released. But secondly, it's always exothermic in the first place because it forms it's the formation of bonds, and bond formation is always exothermic. You might remember bond breaking and bond making, and me saying BMX, bond making's exothermic there. Okay, so it's the formation of the giant ionic lattice basically, and the enthalpy change associated with it. But that's the definition you've got to give. You've got to go from the ions to the solid ionic compound. Okay, the problem with this value though is that the lattice enthalpy, we don't have an instrument or a measurement or a series of measurements that we can take that will enable us to directly determine the lattice enthalpy of a compound. And well, that's important because the lattice enthalpy is directly proportional. Well, it is exactly the same, not even proportional. It is the strength of that giant ionic lattice because it's associated with the bonds in it. And we want to know how strong the ionic bonds are in a giant ionic lattice. That's an important value for chemists to know, but we can't determine it directly. Now, you're hopefully getting a little bit of a callback now from when we looked at a different kind of cycle called a Hess cycle. And Hess cycles, again, they couldn't be determined directly, the values in Hess cycles, so we had to construct that cycle in the first place to determine it. And that's exactly what we're going to do now. We're going to develop a cycle that enables us to determine the lattice enthalpy through an indirect route instead. So imagine that we are going to take the gaseous ions and form the ionic lattice, and that is our lattice enthalpy here. But we need to use other known energy changes to do this, and we do this by constructing a Born-Haber cycle. Haber's the same Haber there who did the Haber process. So where we're going to start actually is not here or here with the gaseous ions or the ionic lattice. We're actually just going to start with the elements that ionic compound in its solid ionic lattice is formed from. We're going to start with the elements in their standard states. And we know that if we go from the elements in their standard states to the solid ionic compound, 1 mole of it, then that energy there, that root 1, is actually just going to be the lattice enthalpy of formation, enthalpy change of formation that you know of, right? The enthalpy change when 1 mole of a compound is formed from its elements with all reactants and products in standard states under standard conditions. But to get from that route to there, there's actually another route that we could go on. What we could do is actually break the bonds in the elements that whatever that's made from to form gaseous atoms, enthalpy change of atomization. And then what we could do is form the gaseous ions. In other words, by doing first or second or however many ionization energies there are to do the oxidation, and then do the electron affinities to get the reduction. Okay, so if we actually follow this route round here, we find out that it's equal to this route here. And what we can do is say, therefore, that route 1 is equal to route 2 in terms of its energy. Okay then, so let's now have a look at constructing a Born-Haber cycle from scratch. So this one here, we're going to be forming sodium chloride as a solid from its gaseous ions, which are Na plus gas and Cl minus gas, so sodium and chloride. And remember that this energy here, the lattice enthalpy, is essentially going to be the enthalpy associated with forming those ionic bonds in the sodium chloride lattice structure. Now, to begin with, when you're constructing a Born-Haber cycle, you put the gaseous ions in and you put the solid ionic compound in. And then what we're going to do is add the elements in their standard states and say that this difference here between the elements in their standard states and the solid ionic compound is equal to the enthalpy change of formation. So sodium is a solid in its standard state and chlorine is a gas in its standard state, and it exists as Cl2. So now what we need to do is work out a pathway going from these elements in their standard states all the way up to the gaseous ions over here. And you'll be given a table of values as well, which will enable you to determine whether the arrows should go up or down. Now, to begin with, what we need to do is atomize these two different elements. And we're going to start with our metal. So I'm going to first begin by atomizing the sodium. And you'll see here we've gone from solid sodium, 1 mole of solid sodium, to 1 mole of gaseous sodium. Now, atomization basically forms separated atoms of whatever that element is. So if you imagine sodium in its solid form, then it's going to exist within this giant metallic lattice with all those strong metallic bonds in it. Whereas if you had sodium in its gaseous form, then none of those metallic bonds are there anymore. So you've got gaseous sodium atoms completely separate where all the forces have been overcome between the atoms. I'm doing this step by step, so you'll notice that I haven't changed the chlorine yet because there's an energy specifically associated with atomizing sodium. So next up, we need to focus on the chlorine. So let's do that. So now what I've done is atomized the chlorine, and there'll be an energy value associated with that. So you can see now I've got chlorine atoms. I've no longer written them as Cl2 because Cl2 represents chlorine with that covalent bond within its diatomic molecule. So a half Cl2 stoichiometrically, yes, would give 1 chlorine atom, but it would be talking about chlorine that's still bonded. And in this case now we've got separated atoms of chlorine with no covalent bonds. Now, of course, if this was a whole Cl2, rather than this half written in front of it, if it didn't have the half written in front of it and it was just Cl2, then you would actually be forming 2 chlorine atoms, right? Because you'd be breaking that chlorine-chlorine bond to form 2 chlorine atoms. So then you would actually need to multiply that atomization value by 2. So it's very important that the atomization value, you use that based off of the number of atoms you're actually forming. And in this case, because we're only forming 1 chlorine atom, I only need to use that value once. If I was forming 2 chlorine atoms, I'd do 2 times in front of that. So now we've got the gaseous atoms. I haven't quite got to the gaseous ions yet. And hopefully from those definitions, you'll remember that the metal needs to be oxidized. So it'll undergo, to form a 1+ ion, it'll undergo its first ionization energy. And the non-metal needs to be reduced. So to form a 1- ion like it is over here, it would need to undergo its first electron affinity, which is basically the same as saying first reduction. So let's first of all oxidise this sodium through its first ionisation energy. And you'll notice now that we've gone from 1 mole of gaseous atoms of sodium to 1 mole of gaseous ions of sodium, shown by the 1+ charge there. And the electron that we've removed from the sodium is actually shown on this list of substances up here. So there's the electron that was removed from the sodium, and it's quite important to show that and not just make it disappear, because we're actually going to use that one electron and transfer it to chlorine to make chloride over here. So we've now ionised the sodium. Obviously, if this was like magnesium, then it would have to also next undergo the second ionisation energy, which would have a different value. So anyway, let's move on and reduce the chlorine now through its first electron affinity to make chloride ions. So I'm going to add that here. So here we've got the first electron affinity for chlorine, and we would go from the chlorine with the electron spare over here, and now that electron's been added to the chlorine to make chloride. So now we've got sodium and chloride ions. So we've constructed now a complete Born-Haber cycle for the formation of sodium chloride. And we can say that route 1, the enthalpy change of formation, is the same as route 2 in terms of energy. Now, when I was doing my A-levels, I never quite understood why. But you've got to look at where you start and where you end up. If I take this route, I start at the elements in their standard states, and I end up at 1 mole of the solid ionic compound. If I start here and follow the red arrows all the way round, well, I end up in exactly the same place. So that's why we can say route 1 and route 2 are exactly the same in terms of energy, because they start at the same place and they end at the same place. So what we can actually say, therefore, is that if we wanted to work out our lattice enthalpy, well, the enthalpy change of formation is equal to the atomisation plus the atomisation of chlorine as well, plus the first ionisation energy of sodium, plus the first electron affinity of chlorine, plus the lattice enthalpy. Well, that's fine. We're basically just saying route 1 equals route 2 there. We're just adding all of these up to complete route 2 because it's made out of multiple values. Well, now that we've got this equation here, well, we can rearrange it. And if we rearrange it, we find out, therefore, that if you take away all of these values here from this value here, then you will get the lattice enthalpy. And that's the basis of Born-Haber cycle calculations. Make sure you read these carefully and have a good idea of what's going on. But essentially, what you're doing to work this out is doing enthalpy change of formation minus all of these values until you get to lattice enthalpy. And you're going to be supplied with actual values for each one of these in order for you to do your calculation. So here we go. I'm going to show you some values here. So we've got the enthalpy change of formation. We've got all of the different enthalpy changes associated with moving towards the gaseous ions here. So atomisation, ionisation energy, and electron affinity. And what you can do is pause the video here, have a quick go at trying to work out that lattice enthalpy and see if you get the same value that I did. Okay, so I got the value of minus 790. So check your value, see if it comes out the same. If it does, great, we're on the same page. If it doesn't, leave a comment below because I am known to make mistakes every now and then. Okay, right then. So let's have a look at ionisation energies now, just to make something really, really clear. So let's say you had below this the elements in their standard state, so magnesium as a solid, and then it underwent the atomisation enthalpy, then you would end up with gaseous magnesium ions. Now, you could undergo multiple steps now in order to get magnesium 2+. So the first ionisation energy would result in you having magnesium positive ions plus an electron. But to get Mg2+, it would need to undergo a second ionisation energy like this, okay? And then you would end up with Mg2+ plus 2 electrons. So that's the way we would show within the Born-Haber cycle. So as part of that whole structure that you've just seen, that's how we'd show the second ionisation energy if it was required. You'll also notice I've drawn this arrow here slightly larger than the previous arrow, and that's actually because second ionisation energies are always a little bit more endothermic than first ionisation energies because you're removing an electron from an already positively charged ion. So we could say that second ionisation energies are always more endothermic as more energy is required to overcome the forces of electrostatic attraction when removing an electron from an already positively charged ion. It's quite important. Second ionisation energies are always a bit bigger than first ionisation energies. So you can show that in scale, the scale of your arrows on your Born-Haber cycle. The same sort of scenario applies for electron affinities, right? So say you were starting with, let's say, for example, you had down here oxygen in its standard state, so it would be half O2 as a gas. And then it underwent the atomization to break the bonds to form gaseous oxygen atoms, and then we end up here. Well, with oxygen, you've got to form oxide, which is O2 minus. So you'll need to actually reduce this twice. So I need to undergo a first electron affinity and a second electron affinity. Well, the first electron affinity is like this. Now, this time, you can see that we're going from gaseous oxygen atoms to gaseous oxide 1 minus ions, which isn't the full oxide 2 minus ions. And you'll notice this time, it's exothermic. Right, why is that? Because previously that enthalpy change was endothermic. You had to put energy in. Well, in order to give, when you give an atom an electron, then actually that first electron you give it is attracted. And because it's attracted, it's a bit like forming a bond. So it's exothermic because the attraction releases energy in that first electron affinity. So you get an exothermic always for your first electron affinity because there's attraction between that incoming electron and the nucleus of the atom. However, when we carry out the second electron affinity, we actually find that this is an endothermic process. And this is an endothermic process because you're giving an electron to an already negatively charged ion. And that incoming electron is going to experience repulsion because you're trying to force it into an already negatively charged ion. So it's not going to want to get near it. You're going to have to put energy in to push it against that repulsion into the ion there. Okay, so our first electron affinity, to summarise, is always exothermic because the incoming electron releases energy as it occupies a shell where it's attracted to the nucleus. So that attraction is a bit like the formation of a bond. The second electron affinity is always endothermic because energy is required to overcome the force of repulsion experienced between the incoming electron and the negatively charged ion. Now let's have a look at some fun examples now of constructing Born-Haber cycles from scratch. We're going to do magnesium chloride to start with, and I'm going to give you some values in a minute and we're going to do some practice calculations. You can just work alongside me on this. So let's start. So I want to form magnesium chloride, and I'm going to start with those elements in their standard states. So I've got them here. Magnesium's a solid in its standard state and chlorine's a gas in its standard state. Now I haven't put a half in front of that chlorine this time because the actual formula of magnesium chloride is MgCl2. So I need to make sure that this is balanced for the ionic compound that's being formed down here, and it is. Now, remember that down here we've got the solid ionic compound, and therefore going from the elements in their standard states to 1 mole of the ionic compound in its standard state, all under standard conditions, is the enthalpy change of formation. So, in order to get another route going on, what I'm going to first need to do is atomise first the metal. So you can see here I've gone from solid magnesium atoms in their giant metallic lattice, to gaseous magnesium ions there. Next up, I'm going to atomise the chlorine. Right, important note here. I'm forming 2 atoms of chlorine. So I need to double the atomisation enthalpy because I'm actually forming 2 atoms there. Okay, important note. Now that I've done atomisation, I need to first do ionisation. First ionisation energy, second ionisation energy for the magnesium to oxidise the metal. Then I have those electrons ready to transfer over to the non-metal chlorine so that after that I can do my electron affinities. So firstly, I'm going to do my first ionisation energy of the magnesium to form a magnesium positive ion, and there's the electron we just removed from it. Nothing's changed on the chlorine because I've associated no energy value with the change yet. But magnesium forms 2+ ions because it's group 2 metal, loses 2 electrons. So I'm going to do my second ionisation now for magnesium, which would have a different value associated with it, remember, because second ionisation energies are more endothermic than first because you're overcoming that attraction. So I've now got an Mg2+ ion and 2 electrons because I'm including the previous electron that was removed in the sum there. So now I've got Mg2+ ions, I now need to transfer those electrons over to the chlorine to form chloride ions. Well, chlorine only forms a 1- ion, So I've only got to do the first electron affinity for chlorine, but because I've got to do it for 2 chlorine atoms to form 2 chlorine ions, I need to do the first electron affinity twice. So just to confirm, there isn't a first and a second electron affinity, because a second electron affinity would be forming a 2- ion, right? And we're not forming a 2- ion, we're forming 2 1- ions. So I'm just now going to do the first electron affinity, but do it twice. So I'll show that like this. So I'm doing 2 times the first electron affinity for chlorine. So one of those electrons is going to go onto one of the chlorine atoms, one of those electrons is going to go onto the other chlorine atom, and therefore we're going to form 2 Cl- ions. Now finally, look at this. I've got gaseous ions of magnesium, and they're the proper ion, the 2+ ion that we know. And I've got gaseous ions of chloride, the 1- ion that we know, 2 of them, which is balanced to form MgCl2. So there's my lattice enthalpy for magnesium chloride. So I've now constructed my Born-Haber cycle for the formation of magnesium chloride. So question 2 here, why did you need to multiply the value of the atomization for chlorine by 2, like this? Why did you do that? Well, there's 2 ions of chloride in the product, so we're going to need 2 chlorine atoms to get those 2 ions, right? So we need to make 2 chlorine atoms, we need to do the atomization of chlorine twice. Now we're only breaking the bond once, but typically the atomization enthalpies are associated with forming 1 atom, right? So effectively half the bond enthalpy. If you're given the bond enthalpy instead, which they sometimes do, then you wouldn't need to multiply it by 2, because if you break the bond, you automatically form 2 atoms. So do keep an eye out for that. It's sometimes a variation on the question type that they do. Next up, we needed to multiply the value for the electron affinity of chlorine by 2. Why did we need to do that? Well, we formed 2 ions, right? So there's 2 ions of chloride, each of which need to gain 1 electron. So we needed to do it twice. Next up, we've got to calculate the lattice enthalpy. Well, you're not going to do that with any of the information here. We need some values. So here's what your values look like. You're given all of these values here, and they give you the symbols in the table. Okay, like this. Now remember, sometimes that H is written before that symbol, like that. Both are correct. So now what we need to do is just basically replace each of these symbols with a number. And if there's a 2 in front of them, like we needed to do for balancing, then you need to multiply that value by whatever number is there. So what I'm going to do now is insert these values. Okay, so we said that root 1, this root here, is equal to this root going from the same position all the way round back to the ionic compound. And we're trying to work out the lattice enthalpy, so we need to rearrange for the lattice enthalpy. And we've written it out like this, and you will be expected to write it out like that in the exam. So deal with it. That's the easiest way of saying it. Deal with it. It's hard, but it's A-level chemistry. And then what we're going to do is plug the values in, and we should get our lattice enthalpy like this. Do take a bit of time right now to read through that, type it into your own calculator, and make sure it comes out the same, because a lot of the time you'll type it in wrong and you'll get that number either positive or negative, and it will just come out wrong. Okay, so we've calculated the value there. Now we're just being asked this follow-up question. Why is the first electron affinity exothermic? So that's saying, why is this first electron affinity here, so that's electron affinity, remember the reduction, exothermic? Well, the incoming electron releases energy as it occupies a shell in which it's attracted to the nucleus. Okay, let's have a look at another example this time. A little bit of a variation on it just to get that idea of second electron affinity this time. So we're going to form magnesium oxide. Right, let's start with our elements. So we've got magnesium as a solid in its standard state. And to form magnesium oxide, which has the formula just MgO with 1 oxide ion in it, then you're going to need half of O2, right? Because O2 is the standard way that we write an elemental oxygen, and it's half of it because we only need 1 atom of it or 1 ion of it in the product. And it's gaseous in its standard state. Well, we're trying to form magnesium oxide, which is a solid. So this enthalpy change between the elements in their standard state and 1 mole of the ionic compound in its standard state would be the enthalpy change of formation for magnesium oxide in this case. So first thing we're going to do is atomize these elements. So let's atomize the magnesium to begin with. So we've gone from the solid to the gaseous magnesium atoms. Next up, let's atomize that oxygen. Well, because I've got half O2 and I'm only forming 1 atom, then I need to do this once. Okay, so I've got my atomization of oxygen. See how it's a lone atom here, no bonds shown in the fact that it's not O2 anymore. Next up, I'm going to need to do the first ionization energy of magnesium. So I'm going to form Mg1+ ions. There's the electron that was removed from it. Leave the oxygen alone for now because we've enacted no change. Next up, I'm going to need to do my second ionisation energy for the magnesium. Here we go. So it's now Mg2+, and that second electron is included in the total for the electrons that have been liberated or oxidised or removed from the magnesium originally. Now what we're going to need to do to form oxide ions, well, oxygen's group 6. So it gains 2 electrons to get a full outer shell. So it needs to form a 2- ion. But we need to show that step by step, right? To form a 2- ion, there's the first electron affinity, and then there's the second electron affinity, which we add up to get the overall value. So we're going to first of all form those 1- ions. And remember that the formation of the first electron affinity is always exothermic. It releases a bit of energy due to that attraction between the incoming electron and the nucleus of the atom. So you can see here that one of those electrons from that pair has gone onto the oxygen. But to form O2-, now what we need to do is add a second electron to form O2- here. So we're going to now force that electron in, essentially, hence the reason it's endothermic, to overcome that repulsion to form the O2- ions here. Okay, so now what we've got, look, Mg2+ ions as a gas, O2- ions as a gas, gaseous ions of those particular elements, okay? And they're exactly the ions we need in order to form that ionic compound. So the final arrow that's going to go down between here and here is our lattice enthalpy for magnesium oxide. So why is there a half written in front of O2? Well, there's only one oxygen in the product, so I don't need a full O2, I need half of O2 if I'm going to balance an equation for the formation of 1 mole of magnesium oxide. Why is the first electron affinity of oxygen exothermic? Okay, well, the incoming electron releases energy as it occupies a shell in which it's attracted to the nucleus. Okay, so the first electron that you give an atom, if you're reducing it, it's attracted. It's like forming a bond, so it's going to release a bit of energy. Second electron affinity, however, is endothermic because the energy is required to overcome that force of repulsion experienced between the incoming electron and the negatively charged ion. Okay, I do word these very carefully. I word them in the same way they come up in the exams, so it's really good practice to try and get used to my wording. I'm not going over the top for the sake of it. I'm just giving the wording that the mark schemes say. Finally, calculate the lattice enthalpy of magnesium oxide. So we're going to need some values now, and we're going to need to substitute those values in. So let's have a go at that. So here are your values for each one of these, and we've got to calculate this value here for lattice enthalpy. Well, remember that root 1, this root here, is equal to root 2, this root from here all the way around to here, including those up downs over here. So we can say this, okay, and then we can rearrange for the lattice enthalpy. Then we can plug in our values and we should get this value here. Now I did animate this quite a long time ago, so please do check my answers and please do leave in the comments below if you're not getting my answer and you're confident that you are right and I am wrong. Fair play. Call me out in the comments, please. Do check these. I want to be called out if they're wrong. Okay, right then. Now I want to do a little bit of recap finally. So let's have a look at those lattice enthalpies. And let's have a look what I've got here. So this is the lattice enthalpy of the magnesium chloride, is it? Yeah. Okay, so this is the lattice enthalpy of the magnesium chloride here, minus 2,528 kilojoules per mole. So what that's actually saying there, let's imagine that arrow was going up. Then you would be going from the solid to the gaseous ion, so you would be breaking that ionic lattice. So if you were to flip that arrow, it would become endothermic. You would have to put in, per mole of magnesium chloride, 2,528 kilojoules of energy in order to break the ionic lattice, per mole, right? Whereas alternatively, I'm just going to skip back and forth quick, the lattice enthalpy for the magnesium oxide was minus 3,237. So to break that bond going between there and there, you'd need to put in 3,000, whatever it was, joules of energy to break the bond in 1 mole of the ionic compound. So you've got to put in more energy to break a magnesium oxide ionic bond than you have the magnesium chloride's ionic bonds in the giant ionic lattice. Why is this one larger than this one? Well, magnesium oxide contains O2- and Mg2+ ions, right? So these ions, the oxide ions in particular, have a greater charge. And ions with a greater charge, 2- versus the 1- of the chloride ions there, have stronger electrostatic attraction. Also, an oxide ion has a smaller ionic radius, so we can say that it's got a greater charge density. So the greater the charge of the ions, the actual stronger the ionic bond ends up being, and that can be shown through the calculations and the results of those calculations that we get using Born-Haber cycles. Oh, sorry, it was animated there the whole time. Anyway. Okay, so we're going to finish off with a little quiz now. Now, I would like you to try and do this properly to see how much you've gathered from this video. So to begin with, if you could just read the question, read the responses, and then come back and see what you got. So lattice enthalpy to begin with. If you haven't paused the video already, please do now. And the answer should be B, the enthalpy change that accompanies the formation of 1 mole of an ionic compound from its gaseous ions under standard conditions. Let's have a look at our next one then. So here's question 2. Please pause and then check to see if you got the answer right. So for question 2, the enthalpy change of formation is, I went for C, the enthalpy change when 1 mole of a compound is formed from its elements under standard conditions with all reactants and products in their standard states. Next one, 3, the first ionisation energy. I went for A, the enthalpy change required to remove 1 electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. Okay, right, next one, 4, the first electron affinity. Have a go. Right, I went for D, the enthalpy change when 1 electron is added to each of the atoms in 1 mole of gaseous atoms to form 1 mole of gaseous 1- ions. Lovely wording there. Right, okay, question 5. Let's have a look. You've got to work out what enthalpy change is shown in this diagram here. Have a look at the change between reactants and products here. Let's see what it was. Okay, so for this one, I went for... Where am I? This is number 5, isn't it? Yep, I went for C. Okay, this is an atomization. To be specific, this is the atomization of oxygen. Notice how it's still a gas, the O2 covalent bond is broken now. Okay, so it's broken, and because we had a half, we only formed 1 atom there. Okay, question 6, you've got to work out what enthalpy change is shown here. Sorry, there should be a line there, but it's you get the point. Okay, have a go at that. Right, I went for A here. This is an electron affinity. I should have maybe given a little bit more information here. This is specifically, it's a first electron affinity because you're only going from O, gaseous, to O-. Remember, oxygen's then got to go a second electron affinity to form O2-, which would then be endothermic in that process. Okay, so that one should be for question 6A. Okay, 7 then, try and work out what this enthalpy change is. Okay, I went for A here. This is an enthalpy change of formation because we're going from the elements in their standard states to 1 mole of the ionic compound. Okay, let's have a look at 8 now. The second electron affinity is always, let's have a look. You should have gone for B here. The second electron affinity is endothermic because it's going to require energy to force that electron in, overcoming the repulsion of an already negatively charged ion. Okay, number 9 next. Okay, so for 9, the second ionisation energy, you should have got as C. It's more endothermic because it requires more energy to remove an electron, overcoming that attraction from an already positively charged ion. That attraction is going to be stronger if the ion is already positively charged to remove that second electron from it. Okay, finally then, question 10. Let's have a look. So we've got to work out which equation fits the gap. Be very, very careful here. Okay, right, so we can see it's undergoing the second ionisation energy, which means it's happening for magnesium. You're going to form a 2+ ion, so that instantly discounts D because it's not forming a 2+ ion. So then we've got to decide between the rest. So for me, it appears that the correct answer is D. Now, you might have thought it was B, but B didn't include state symbols, and state symbols are absolutely essential in Born-Haber cycles. Otherwise, there's no point talking about things like atomization because you wouldn't have been showing a change. But anyway, this is an ionisation energy, so it should have been D. Notice how Mg has become Mg2+. It's still a gas. Now you've got that second electron adding to the first there, and the oxygen is still a gas. So there's only ever one change shown at a time in a Born-Haber cycle. Okay, so that one should have been D. Now, I'm just plugging a brilliant website. I have no affiliation with this website at all, but chemguide.co.uk has an outstanding guide, not only on this topic, but pretty much all of your A-level topics. And I really do encourage you to have a read up on this link here. If you just type in Chem Guide, Lattice Enthalpy, it'll be the first link that comes up. This is a really great website, and I do recommend that you give this a read if you get stuck with any of the practice questions that I've supplied you with. So thanks very much for watching, and I will see you in the next one.